Thanks for that introduction. So what I'm going to do is expand a bit on the lightning talk that got me here in the first place and talk about a few additional technologies and also sort of framework for thinking about being successful in exploiting big data exploitation. I think it's important to recognize that there are different use cases for big data exploitation that have different requirements. In the upper right-hand corner where I have integrated data warehouse, I'm describing the capability required to essentially productize the data, right? So the BI analysts in a company want answers to business questions, and this upper right-hand corner, this is very service level driven. So if I want the answer to a business question, I have certain expectations about the quality of the data. I have certain expectations that the data was loaded this morning by 6 a.m. or every hour, or every 15 minutes. I expect high performance. I expect high availability. It's very service level driven, right? That's very different than the requirements we find that the data scientists have. And data scientists are different than the BI analysts because the BI analysts are really using data as a product. The data scientists are not interested in the answer to a business question. Sounds a little bit funny, but they're not interested in the answer to a business question because they're looking for the questions. And that's very different. So they're doing much more exploratory work. They tend to be much more aggressive in using advanced statistical analysis and visualization and so on. And while they care about service levels, while they care about quality of the data and performance and all those things, I would argue they care less about service levels than they care about power, flexibility, and especially agility, right? If you look at the amount of work, effort, time it takes to get data into the data as a product infrastructure, it's not unusual that it would take 90 days to bring data in. You do an integrated data model, you do data quality certification, you make it auditable, you do all those things. If it takes 90 days to get new data into the sort of data R&D part, you're dead, right? 90 minutes, I want 90 minutes, not 90 days. So as a data scientist, I need to be able to self-provision the data into that environment. And I want to be able to use capabilities that go beyond just SQL processing. SQL is great, we like SQL, but it's not enough. We want to be able to do graph processing and text processing and advanced statistical analysis and other things that go beyond just pure SQL processing. Power, flexibility, and agility, right? On the left-hand side, I show the data reservoir. I know in the industry you use this term data lake. I don't really like that term. Lakes are random acts of nature. I prefer something that's man-made for a purpose. So I call it data reservoir. And the main point of data reservoir is that represents the raw materials. The raw materials for the data R&D, right, that I'm going to provision from. Also, once I find the pot of gold after the sort of iterations in data R&D, I'm going to use the data lake or data reservoir as the basis for provisioning data into data product as well. Okay? And in the big data philosophy, all data has value, we just haven't found it yet. So if you throw it away, you can never find it. So we should keep all data forever in the data reservoir. Now, all in forever is relative to your budget, of course, but one of the key criteria to be successful with the data reservoir is we need to be very low cost per terabyte, and we also need to be able to support not just traditional record-oriented data, but also sort of non-traditional data, right? So those are the two criteria. So if we look at the different areas for big data exploitation, data as a product, the upper right-hand corner, right, with the integrated data warehouse, service level driven. That's what I mainly care about, right? The bottom right, data R&D, that's about power, flexibility, and agility, right? On the far left, the data reservoir, that's about low cost per terabyte and support for multi-structured data, right? Very different criteria. And of course, they all have to play together, and it's one ecosystem. Oliver talked about this yesterday in terms of this ecosystem concept, and we'll come back to it. Now, this talk, at least in the title, is about technologies for successful exploitation, but I think it would be remiss to leave out governance, because I think we, at these conferences, talk a lot about the technology and we don't talk about the hard stuff, which is the governance part. So I'm going to have a few words at the end about governance as well, but mainly focus on the technology. So we look at technology, I'm going to focus on 3 areas. So we'll focus on multi-temperature data management, because I want to be able to support cost-effective deployment of the big data, right? I remember at a previous version of XLDB, the last one, in fact, there's a guy from Facebook up there talking about analytics and exploitation and big data and so on. And somebody asked him about, putting everything in memory. And he said, well, we're a free service. We can't really afford that. It's not really viable. It's a nice thing to think about with an infinite budget, but it's not viable. So for big data exploitation to be successful, it has to be economically viable. And I'm going to argue that to do that, we need to have some version of multi-temperature management. And I'll sort of show you some architecture thoughts about doing that. The second point is polymorphic file systems, right? Yesterday, Paul Brown talked about the importance of schema. Okay? And I believe that very strongly, but I don't believe that relational schema is the schema for necessarily everything, right? Because we might want to represent graph in a different way than we represent a record-oriented structure, which might be different than how we represent text and so on, right? So I'll explain more about polymorphic file systems. And then lastly, late binding. So this is where I'm going to diverge a little bit from what Paul talked about yesterday and talk about schema on read rather than schema on write, and what some of the interesting trade-offs are in that space. Okay? So on the first topic, multi-temperature data management, it's very clear that the desire for data and more data and faster data outpaces Moore's law, right? So going back to the Facebook talk from the previous XLDB about putting everything in memory, right? In the industry, there are some who talk about put everything in memory because the cost of memory is going down, and it is, right? About 30% every 18 months, cost of memory drops, and it compounds. So that's, gets cheap fast when you compound 30%. And yet, the people that talk about this are usually in marketing, not in engineering. And they use what I call marketing math, right? So marketing math, I'm an engineer by training, and real math, there are 2 sides of every equation, right? So one side of the equation is cost of memory is going down by 30% every 18 months. Absolutely buy it. It's a correct number, more or less, right? The other side of the equation is very important, right? What's the other side of the equation? How fast is your data growing, right? And when we look at the next wave of big data, right, it's going to be all about the sensors, right? And the sensors are going to generate more data than we've ever seen before, right? And it goes to the point that Paul was making yesterday. When machines are generating observations, the volume of data created far outstrips, right, anything that can be created with humans clicking and blogging and all this kind of stuff. It will dwarf everything we've ever seen before, right? And so with that volume of data, right, that's going to be created, there will be data created at a much higher rate than the cost of memory is going down. So it's unsustainable to think about putting everything in memory. On the other hand, we like memory. It's fast, right? It is getting cheaper. And so this chart I used in the original lightning talk that got me here, but I think it's worth putting up again because we need to remind ourselves that not all data is created equally. Yes, we've got a lot of it, but less than 20% of the data is accessed more than 90% of the time, right? So that data I absolutely want in memory, right? But taking the 80% of the data that represents less than 6% of the IOs, putting all that in memory, Not so smart. Economically, it doesn't really make a lot of sense, right? Assuming that we're working with large volumes of data, right? If it's 80% of 100 gigabytes, then who cares? Put it all in memory. But when we're talking about 100 petabytes, then it doesn't make any sense, right? And so the idea is that we want to optimize for both cost and performance simultaneously. So I want the hot data, the data that's accessed very frequently, I want that to be in the lowest cost per I/O storage, which is memory, right? For the data that's relatively cold, I want that in the lowest cost per terabyte memory, right? Because I'm not so concerned about the I/Os. It's cold data I'm not accessing very frequently, but I want a low cost because I want to store lots and lots of data in an economic way. And so that 80%, I want that in the lowest cost per terabyte, and that's going to be electromechanical storage, at least for the foreseeable future, okay? So when we look at building a massively parallel processing system for extreme large databases, we want a storage hierarchy, right, of some kind. And the key point here is, any competent hardware vendor can build a storage hierarchy that looks something like this. It's not hard, right? The hard part is not the hardware, right? So when I was at MIT, the person that I learned a lot from architecture about, he would say in class, hardware is the easyware, software is the hardware, right? The software needs to figure out how to do the placement of the data automatically with no human involved. You'd be willing to send your best DBA away for 2 weeks and figure out what is the hot data and the cold data, right? And then map it to all the sort of appropriate storage devices in the hierarchy that I'm showing you. The problem is by the time she gets back, she's wrong, because the temperature of the data is changing all the time. So it can't be a static thing. It has to be done constantly with no human intervention, right? So this auto-migrate part, this is actually the hard part. It's not building the storage hierarchy. It's the software to do this auto-migration, right? No hands migration, no hands optimization. And this storage hierarchy that I'm showing you, it's going to change over time. It already has changed. The fiber channel drive's obsolete, I would argue. I know you've got a lot of them in your data center today, at least some of you do, but this is obsolete technology. The price performance doesn't justify its existence anymore, and it will go away, right? And today, this flash memory is in many cases deployed as solid-state disk drives. That's a really inefficient interface for getting access to flash memory by using I/O subsystems designed for disk drives, right? So flash memory will be replaced by flash shelves and other things. So there'll be some interesting evolution here, right? And the ratio of in-memory and flash memory and electromechanical drives, this is going to depend on the cost per terabyte and the cost per I/O, and it will change over time as the economics evolve, and that's great, right? And we should be able to deploy in appropriate ratios based on where the economics are at a particular time. So in the future, we'll have these storage hierarchies, and they'll be managed automatically, but there will still be, I'll say, special cases where you'll have niche performance requirements, right? So extreme performance appliance, you might have something 100% in memory because it's a relatively small amount of data, and you want very high performance at any cost, and it's fine, right? And so there will be 100% in memory, right? Or at least memory and flash together. And then there'll be data that you just don't care about performance, but you want to keep it all forever, and so cost per terabyte is the main driver. Right? And so that will be the extreme data appliances. And so there'll be combinations of these things. And then it comes to the ecosystem about how to sort of make them work together, et cetera. Okay? The second technology that I want to talk about is polymorphic file system. Right? So polymorphism, this is a It's a funny word, right? Even if English is your first language, it's a funny word. It means that you can change shapes to adapt to new situations, right? And the word may not be in your normal vocabulary, but your 6-year-old kids understand it, right? Because they have these toys called transformers, and the transformers can change to adapt to things. That's what we're talking about here. A file system that understands that there are different types of data which are adaptable or most effective in different kinds of schemas and different computational models, right? So of course I can take a graph and kind of shove it into a relational model, right? Everything's Turing complete. If I do enough work, I can make it do what it's supposed to do, but it's painful to use and the performance is maybe not where you need it to be. So we need to be able to store data in a native form with structures and processing models that are appropriate to the data that we're working with. So if we're doing social network metrics, there's a whole different set of mathematics aligned to graph processing that's very interesting. And we'd like sort of models that allow us to do that. Schemas allow us to store graphs effectively, and the mathematics to allow the calculations to be done effectively. And it needs to scale, right? I need to be able to take the over 10 billion LinkedIn connections across over 350 members of LinkedIn and do all kinds of interesting analytics, right? So these cases where we take the data and we assume that all the data fits into memory, these are toys, right? And there's a lot of toys out there, right? But if we're talking XLDB, this is a conference about XLDB, we cannot assume that any reasonable implementation that everything fits into memory. Okay? If it does, great, we should be able to exploit the memory. We should be able to deliver performance on as much memory as we have, and we should be able to use the memory intelligently, right? But we cannot assume that everything fits into memory. And so I reject these models where you throw everything into a file system, a stupid file system, and then we depend on sucking everything into some memory structure in order to get performance. This is really not sustainable for XLDB implementations. It's sustainable for toy problems with small amounts of data. The last example I wanted to use is is around late binding and taking a very simple example of weblog data, right? So this example looks very ugly, right? And you say, there's no structure in that. But if you were an Apache weblog expert, you would say, actually, there's a ton of structure in that. You just have to look closely, right? And if we were to use traditional ETL processing, we would map all of those fields with an ETL programmer sitting next to an Apache weblog expert, and we would map it into this structure, something like this. Okay? The problem is that every day someone's changing their mind about adding new tags to the website and collecting new data, and alter table and reloading tables and all this kind of stuff. It's just too ugly. It's just too ugly. And as soon as you have to ask a DBA to do anything, it's too slow. Right? Not slow computationally, but slow process-wise, right? So the example here, taken from eBay, is that, the data that we know is going to be there, we'll map it into structured fields because we get value from having that sort of structure at write time. We get performance and other advantages from that. But there's some stuff that I just don't know what's going to be tomorrow. So I'm just going to throw it into a CLOB, a character large object, and I'll go figure it out later. At read time, at query time, right? And nowadays, I'd probably throw it into some kind of a JSON structure, some variation on that, right? And then I'll go manipulate that and pull out the data that I want at query time, right? And so I'm taking this JSON structure and I'm pulling out the list of items that were returned by a search from somebody, looking to buy a 1974 Mustang or whatever it is that they're looking for. And then I'll normalize that list and aggregate to figure out which are the top items that people search for on January 1st January 18th of 2015, right? And in this example, and this is a real example, I'll cover up some of the actual number results. This table, the event table, is over 4 trillion rows in size. On a daily basis, there are over 8 billion rows, and in each row, we've got these, can be lots and lots of attributes and search items and so on, hundreds of attributes of interest in each one of those rows, stored in an object form. And querying that, right? Querying this over 4 trillion rows with over 10,000 unique things that could be in each row, right? This comes back in 32 seconds with no indexing, right? No indexing. Now, I will point out that we're not actually scanning all 4 trillion rows, right? Because there's daily partitions, and I only asked for 1 day, so I'm really only scanning 8 billion rows, not 4 trillion rows. But I am fully parsing and pulling apart the item and doing all the normalization and pivoting and all that kind of stuff at runtime. So the kind of stuff that you normally do with ETL processing at load time, we're actually doing it at runtime, right? And that has some interesting implications, right? It makes data modeling a lot easier, right? But all you're really doing is kicking the can further down the street and making it somebody else's problem, right? If you don't do data model, if you don't introduce a schema, somebody eventually has to understand the data. And I was talking with Paul about this yesterday, and he said, well, I've never met a case where where people want to do this kind of thing, where the reason why is because they didn't understand the problem that they were solving. And I actually think that's correct. Okay? And the reality is, many cases, they don't understand the problem that they're solving, particularly people that are bringing the data in. Later on, some smart data scientist is going to think of some questions, and they're going to query into the data, but that you don't know in advance. So it gives you a lot of flexibility. Right? But there's a price that you pay because you're, instead of doing all the work at load time as part of an ETL process, you're doing it on every query. How much are you paying? Well, there's some interesting trade-offs there because you store as an object, you don't have all the joins that you might have in a normalized model, right? Yes, there are data quality issues that can be introduced, as was pointed out in yesterday's session. So you have to have some way of validating, some sort of external way of validating the structure of the data and the quality of the data and so on. You save the joins, but you pay some extra processing for doing the transformations at query time, right? But that's a reasonable trade-off for the subset of data where you really don't know all the questions that you're going to ask. And depending on the efficiency of the JSON implementation and so on, you can probably get that down to double-digit percentage differences, right? I mean, if it's 10 times the price, then clearly you're not going to do it. Right? But if it's 20% trade-off for that extra flexibility, then you probably are going to do it. Then that's a reasonable trade-off. Okay? The biggest problem on this schema on read versus schema on load, if we do the schema on load, the BI tools that are out there in the marketplace, they generally understand what to do with the data. They could generate SQL or JSON path or whatever. Schema on read, the BI tools today, they don't know how to deal with it. Right? And so you end up writing the code yourself or embedding crafted stuff into the BI tool in such a way that you're really not using a point-and-click interface for getting access to the data. Now, the data scientists probably don't care because those graphical user interface tools, those are like training wheels, don't need it, right? But if you want to productize this stuff and you want it sort of accessed by the masses, then you need the BI tools to work more effectively. So just a couple of words on governance before I close out, right? This comes from the work from the Jim Gray on fourth paradigm, sort of based on his lectures and so on. There's a book written out of Microsoft, which is downloadable and pretty interesting. And we talk a lot about capturing the data, right? So get all the data into the data lake, right? We talk about the analysis, right? Go get the value, right? We don't talk enough about the curation, right? So the curation part, where we find the right structure, spend the time to figure out what schema makes sense, create the metadata, understand the lineage, all those kinds of things, we don't do enough there, right? And Gartner last month actually published a report suggesting that through 2018, 90% of all deployed data lakes will be useless because we're dumping data in, but we have no idea what the data is. We have no idea how to get the value out. Right? The chief technology officer for a very large North American bank, he told me in a conversation, we love Hadoop because we can store all data forever at a very low cost per terabyte. But we hate Hadoop because the only people that can get the data out are the people that put the data in, right? So we're creating these swamps, right? These data dumps that we're having a hard time getting the value out in a sustainable way, right? And so, managed means something like this. A lot of what's being built is stuff like this, swamps that you would not want to bet your career on. Right, Hadump, I've sometimes heard people call it, right? Just dumping the data in with no curation, no metadata, no nothing, right? So curation is important. We need to know where the data came from. We can't just be writing a bunch of scripts and loading files into some infrastructure, not keeping track of what instrument created them and what were the scales that were used to do the measurements and when was it done and who did it and all that. We need all that provenance, audit trail, lineage, whatever you want to call it. We need it because if we don't have the right information about how the data asset is created, then its value goes down because then the only person that will use it is the person that put it there because nobody else trusts it, right? And nobody else really knows, for which use cases it makes sense to leverage this data, right? And so basic questions of provenance, we're not very good at answering on a lot of data, particularly in the data lakes or data reservoirs out there, right? This is basic stuff, right? And I was at Informatica World last week, and one of the big topics of conversation was how to create a universal metadata catalog, right? How do we get that across the different technologies and so on? This is really important stuff. Right, and not enough people are spending the time to build out that capability. Right, we're spending a lot of time dumping data into Hadoop, right, because it makes us feel very important that we've got more petabytes than the guy next to us, right? But we're not actually investing in making that data usable. Right? And if we don't have the provenance, if we don't have the lineage, then it's very difficult to reproduce results. We can't collaborate effectively because it becomes my data set rather than the enterprise data set. Right? My data set, only the person that put it there will be able to use it effectively with the knowledge of sort of what are the range of constraints on that data. So in the new world, ecosystem wins, right? There will be multiple technologies in each of those areas. There may be multiple technologies in your data product, in your data R&D, as well as in your data reservoirs. There'll be multiple technologies, and getting them to work well together is important. So metadata solutions that solve for only one particular technology, not very interesting. Right? We really need them to cross the boundaries of the technology to truly be universal in facilitating the collaboration. We want to have architectures that allow us to use the right technology for the problem that we're solving. Right? There's no one technology that will handle all the data in an effective way, cost-effective as well as productive for the data scientists and the BI analysts. So we need these pieces to work together. These are the problems that we need to solve as an industry. So with that, I thank you very much for spending this first part of your morning with me. Thank you.
So we have a couple of minutes for questions. Are there any questions?
Can you say just a couple of words about the different data structures that you think are needed for graph data?
Can you repeat
the question was asking about the structures needed for graph databases in particular. So I think that the main thing is that obviously, there are different representations of sort of, edge vertice models and so on. The main point is that we need to understand that in real graphs, the edges are not uniformly distributed across the vertices. And so naive models, which I'm assuming that we want to be able to partition so we can get good parallel processing and so on, we need to be smart about partitioning, not just partitioning on vertices, because there will be a small number of vertices which have a dominant number of edges. So we need to have models that for most of the vertices, which have a small number of edges, we can partition on the vertices, but the other ones we need to sort of be able to figure out how to sort of partition on edges in such a way that we get good sort of parallel processing in a shared nothing model. All this, of course, for me as a data scientist should be invisible. I shouldn't care about any of that, right? And I should have sort of computational models that execute in parallel. So the bulk synchronous processing models, I think, are the right thing as long as we get the partitioning right.
I've got a question. Do you have any observations about, so you were talking about a polymorphic file system, about integrating multimodal data. For example, in healthcare applications, you might have time series of glucose levels and other physical measurements. You might also have prescription records and other health records, all of which need to be brought together.
Yeah, so the point of the polymorphic file system is exactly that. So healthcare is a great example because I've got an electronic medical record which have text of physician notes, and right next to it I have an image of a CAT scan, and then I have, in your example, the sort of time series data of a diabetic's glucose measurements and so on. So you really want to be able to sort of have a complete view of that electronic medical record, even though there are sort of multiple data types in there. Now the question I think that comes to mind is, should that be multiple systems, right? So one that's specialized in text objects and one that's specialized in image objects and one specialized in time series, and then we sort of interoperate between them, but there's a cost to doing that because optimization across those systems is very, very hard, right? So ideally, I would like to have more integration of that data into a single polymorphic file system that allows those to coexist. And then the optimizer can be a lot smarter about how it sort of goes in and reaches in and get the data. This is, I think, a problem that we have not solved yet in our industry. And the reason for raising it here is to get people to think about it and hopefully do interesting things.
So last question over there.
In the beginning, you mentioned that data scientists are not really answering the business questions, but they're looking for the questions that are not known. Can you elaborate a little bit more? Do you mean that they're actually formulating a bunch of hypotheses and trying to prove or disprove those, or
yeah, so
what do you mean?
That bottom right-hand corner of the picture is the so-called data R&D. The data scientists are basically running experiments with the data to validate or not their hypotheses to see where the interesting stuff is. And so a data scientist will typically fail. 9 out of 10 hypotheses will be wrong, but they learn from each one and eventually you get to the pot of gold. So this fast iteration and agility is really, really important in being able to sort of try out new data. And I don't need the data to be perfect, and I don't need it to be fully modeled, because data scientists are usually technically savvy enough that they'll torture the data to get it to tell them what they need it to. And it doesn't need to be perfect. They just need to sort of get directionally correct on where are the interesting patterns and relationships in the data. And then when we productize it, we can worry about making it easier. Thank you very much.
Thank you.